Welcome to this lecture series on pulse width modulation for power electronic converters. So far we have covered several modules in this course. One of the first modules we covered was an overview of power electronic converters, different types of DC-DC converters and DC-AC converters, including voltage source and current source and multi-level converters, neutral point clamp converters, flying capacitor and so on. And then the second module was on applications of voltage source converter such as motor drive, active front end rectifier and reactive power compensation, etc. Then we looked at some principles, preliminaries of pulse width modulation. Then we looked at generation of pulse width modulation at low switching frequency. How do you go about doing it when there are very few switching angles in every fundamental cycle? So, we looked at things like selective harmonic elimination, for example, and some offline optimal PWM. Then we looked at this generation at higher frequencies, that is this is triangle comparison. You compare some 3-phase modulating signals with a carrier whose frequency is much higher than the modulating signals frequency, and you produce PWM waveforms. The same way you do it with the space vector. There is a revolving voltage vector given as a reference. You sample that every time and you use your inverter as different vectors produced by the inverter, and make sure that the inverter produces an average voltage vector which is equal to the reference vector. Same thing done in space vector. We have looked at what are the differences. We have seen that space vector based PWM is more general than that. Both continuous and discontinuous PWM methods can be implemented either using triangle comparison or space vector, but the so called advanced bus clamping PWM methods are actually space vector based PWM methods. So, after the PWM generation we were looking at the analysis, we were looking at the waveform quality. The primary thing in the waveform quality is like RMS current ripple. So, we looked at how to analyze the current ripple in this space vector domain. Then we looked at the DC link current. So, how do you calculate the RMS DC link current, and from there the capacitor current. So, the RMS capacitor current, as I mentioned, is important for sizing the capacitor. Not only that, that is an important input for evaluating the loss in an electrolytic capacitor. So, in the electrolytic capacitors you have certain some amount of loss happening, which is represented by what is known as the equivalent series resistance, ESR. So, once you know the RMS current, you can square the RMS current and multiply by ESR to get a some measure of how much loss could be expected inside the power the electrolytic capacitor. So, in some sense we have started on those things, like we know that, for example, if you know the RMS line current ripple, so you can find out what is the copper loss in the series elements. For example, if there is a line inductor, the line inductor would have some internal resistance. So, this RMS squared multiplied by that would be the additional copper loss on account of these harmonic currents. And this DC link current, and from the DC link current you can evaluate the capacitor current. The RMS capacitor current gives you a measure of what is the capacitor loss. So, we also analyze the torque ripple which are related to the line current ripple. Now, like you have a measure for the loss in the capacitor, you need losses in the other places, that is main things are losses in the semiconductor device. So, that is what we are going to look at today or in this particular module. So, evaluation of inverter loss. So, once we have done with the evaluation of inverter loss, up to this point we have actually been dealing with idealized inverter. We have not really looked at anything on the non ideality significantly. So, here is when we start looking at the devices were regarded as ideal devices. Now, we are going to say that we are going to start looking at the devices as practical devices. So, practical devices will have certain amount of power drop when they are on, and they will take finite amount of time to turn on and turn off. They will have certain amount of switching energy loss and so on. So, we will try to calculate the conduction and the switching energy loss. The further modules to come would be the effect of the inverter dead time. So, what is that? As I just mentioned, practical devices take a finite amount of time to turn on and turn off. So, the devices in one leg are switched in a complementary fashion. So, one device is turned off and the other device is turned on. Now, since there is a small possibility that both of them could conduct concurrently, because it takes some finite amount of time for the devices to turn on or turn off. So, what we do is we first turn off the device in one leg. The device which is to be turned off is turned off first, and then the next device is turned on. So, the gating signal to the incoming device is delayed by certain amount of time, which is called as this is dead time, and this dead time has an adverse effect on the inverter's output voltage waveform, and that is what we call as the dead time effect, and we will talk of how to compensate for that. So, from this point onwards we are looking at non-ideality. So, one of the effect of the non-ideality is the inverter loss, and then otherwise the dead time and the effect of dead time, and here we would look at over modulation. So far we are looking at situation where the modulating signal's peak value does not exceed the carrier peak. So, you will have a situation if the modulating signal's peak exceeds carrier value, that is over modulation. So, we will look at over modulation, and then finally we would look at a few PWM methods for multi-level inverter, which would be the end of the course. So, now over to this today's module. What we are going to look at is, we are going to look at ideal and real switches. So, all along we considered the switches to be ideal. So, what do we mean by ideal and what do we mean by real switches? What are the differences? So, one of the differences in the forward characteristics, there is a certain amount of forward drop. So, we would look at how the forward drops of the different devices can be modeled. Then we would try and see how to calculate conduction loss, because in the forward drop is considerable, the switch, this ideal switch, there is no loss, because when the current it is conducting, the voltage is 0. When it is off anyway, the current is 0, but in a practical switch, when it is conducting, there is a small forward drop, and therefore there is a power loss, there is some voltage into current is non-zero. So, there is some power loss, and that is what we call as conduction loss. So, we would try to evaluate this conduction loss, and as you can understand, this conduction loss could vary with PWM method to PWM method. So, we would quickly discuss these PWM methods, which we have, of course, we have discussed before. We would try to see how the conduction loss would vary from one switching PWM method, or how to really go about calculating the conduction loss for the various PWM methods. Then we will look at the turn on energy loss and the turn off energy loss. When a device is turning on or turning off, that is in one leg, one device turns off and the other device turns on, there is a certain amount of energy lost. So, what is that? We will look at that in the thing. This is most probably such things we will get into the next class in greater detail. So, this class would focus, this lecture would focus more on the conduction loss part. Then we would evaluate the switching loss for the various PWM methods, and we will come up with a simplified evaluation of switching loss, and we will finally present some design of PWM method which will reduce the switching loss. That is, we will look at some PWM methods which will, particularly we would look at these advanced bus clamping PWM methods and see how switching loss can be reduced using these advanced bus clamping PWM compared to conventional space vector PWM. So, now we get started with the exact topic for today, which is conduction loss in a 3-phase inverter now. So, you have this, as I said, all these days we will discuss them as ideal, and the last lecture we looked at evaluating the current through this, and once you know this current and once you know this current that is flowing from there, it is possible for you to evaluate the capacitor current. So, the capacitors are often modeled like the last class we did. So, we tried to calculate this current, what we call as IDC, and then we calculate this current I capacitor. So, if you look at the various sources for losses, you will see that for example, capacitor also there are losses, and that can be represented by what is called as ESR of the capacitor. So, you will have what is called as ESR of the capacitor. So, whatever is the mean square capacitor current, that multiplied by ESR would give you the amount of power that is lost in one particular capacitor. So, you can actually evaluate the losses in the capacitor. These further lead to temperature rises, etc. There are capacitor models available which can actually help you study how much temperature rise could be expected for given amount of power loss. In fact, from this power loss and temperature rise, there are also some estimates for lifetime is also available, which are all available there in the literature for you. Okay, now, but we are not directly dealing with such things here. So, this is ESR. So, this is one component of the total power loss in an inverter. There is another component of the power loss that you may have in an inverter is, I will just draw it in maybe a different one, or the same color is fine. So, there will not be a voltage balance here. So, what you will normally do is you will have some resistors connected like this, some resistors connected. What would be the purpose of these resistors? To balance out the voltage. So, there will be some amount of difference, these two capacitances. We say there is 0.5 VDC, this is also 0.5 VDC, it may not be exactly so. So, if it is 600 volts, this is ideally should be 300 and 300, but this could be 320, this could be 280. As long as if it is small, it does not matter, but if it becomes larger, it is going to matter. So, what we do is, we would look at, we would try to make sure that. So, sometimes you may have a situation that one capacitor has higher voltage and the other one lesser one, and therefore, it can even eventually lead to kind of stress on a particular capacitor and even a damage of that capacitor. So, we would ensure such kind of resistors, bleeder resistors they are called, which will make sure that there is certain amount of power sharing. So, this serves the good purpose of ensuring that the voltage sharing between these two is very good, but then the bleeder resistors themselves will dissipate certain amount of power. So, if your total resistance is, you call it as RB, this is VDC. So, VDC square upon RB would be your power loss in the bleeder resistor. So, this power loss in the bleeder resistor is one component, and the power loss in the electrolytic capacitors itself is another component. So, these are some components that of losses that you will have here. Then the major losses that actually occur are going to occur in these devices. So, the result of these losses is that there is going to be heating up, the junction temperature, the semiconductor inside would get heated up. So, if it gets heated up, it will not function okay. So, we have to have an arrangement for dissipating all this heat. So, what is normally done is, you connect it on a heat sink. Every device is normally, you never use these kind of devices without putting them on heat sinks. So, you may have large heat sinks. So, sometimes the devices may be mounted simply on heat sinks, sometimes they may be mounted on heat sinks where with air blowed between the pins of them. So, which is called forced air cooling. So, there is natural air cooling, there is forced air cooling. So, you have certain cooling arrangements which will make sure that this thing. So, even with the cooling arrangements, you have to make sure that the device junction temperature does not cross something like 120 degree Celsius, which is taken as the safe junction temperature for many of these such devices. Alright. So, we now look at, if you want to calculate what the junction temperature would be, because you have to make sure that the junction temperature has got to be low. So, you have to make sure that the loss is low, low enough that it can be safely dissipated now. So, if the loss has to be low enough to be dissipated, you should know how to calculate the loss, and the loss has these components of conduction loss and switching loss, which is what we are going to look at now. So, we have first ideal switches. Ideal switches have 0 on state drop and they have no conduction loss, because when it is conducting, the loss is 0, I mean the forward drop is 0. So, the product of voltage and current is 0, therefore, conduction loss is 0. So, when if you are looking at the leakage current, that is in the off state, is there current through the ideal device? A practical device may have some small amount of current, what is called as leakage current. An ideal device has no leakage current flowing through it, 0 leakage current, there is no off state loss. And when it turns on, an ideal switch turns on instantaneously, and similarly it turns off instantaneously, and there is no energy loss. Maybe when it turns on or turns off, the voltage collapses immediately and the current rises immediately when it is turning on. So, there is no instant when both voltage or current are high concurrently, and it does not have any significant energy loss during this, no energy loss during switching transitions. This is an ideal switch, but you use devices like MOSFETs, IGBTs, etc., which are practical switches, they have a finite drop. So, you will have a drop across the drain and source terminals in a MOSFET, the collector and emitter terminals in an IGBT. So, you will have some drop. This drop multiplied by the current is the instantaneous power that is being dissipated in the device, and therefore, there is something called conduction loss. So, this on state loss, the loss that is suffered by the device during the on state is what is termed as conduction loss. Thankfully, when the device is off, the leakage current is negligible. There may be some leakage current in a practical device, but it is negligible, and the off state loss is also negligible. At least the off state loss is too slow compared to the on state loss and the switching loss, therefore, it is negligible. But it takes a finite amount of time to turn on, as I just mentioned a while back, and again a finite amount of time to turn off. So, switchings are no longer instantaneous, and as it turns on, what do you expect? You expect the voltage to fall and then the current to rise. So, but the current would start rising before the voltage has fallen significantly. So, what will happen at certain or during the switching intervals, both the voltage and current are high concurrently. So, this leads to significant amount of energy loss. So, that is what you call as turn on energy loss. Similarly, when the device is turning off, it takes finite amount of time. So, during turning off, what do you expect? You expect the current to fall and then the voltage to rise. Before the current has fallen, the voltage rises. So, there is significant amount of both V and I, V across the device and current through the device during such transition. So, that leads to certain amount of power dissipation during that, and there is an energy loss over the switching interval. So, you call that as switching energy loss or whatever. So, there is a significant amount of energy that is lost during turn on and turn off now. This is something which we might focus a little in the next class. So, we are going to evaluate this conduction and switching loss in an inverter, that is our task now. So, if we can evaluate this, we will know how much is the loss, and then you can go about calculating what are to be done subsequently. So, you have this, what are they, go by individual devices, there is MOSFET, there is IGBT, there is diode. So, if the MOSFET is conducting, what is the relationship between the voltage across the MOSFET and the current through the MOSFET? That is what is called as the forward characteristics. Relationship between the forward voltage and the forward current, that is when the device is conducting, what is the voltage drop vis-a-vis the current through the device. In case of a MOSFET, the voltage across the MOSFET is proportional to the current through the MOSFET, and therefore, the MOSFET can be modeled as a resistance. It is as a resistance between its drain and source terminals during the on state, and it is popularly represented by the symbol RDS on. R stands for resistance, this is a drain to source, and on is the on state. So, you call it as RDS on. So, MOSFET can be modeled by this value. So, there is certain ratio of V by I, VDS by ID, and that is equal to this. If it is an IGBT, an IGBT's voltage, the forward characteristics can be modeled by, you can consider the IGBT to be a voltage source VCE in series with the resistance RCE. So, this can be a model for your IGBT's thing, but this can be simplified. For sake of simplicity, you can just simply consider it to be a voltage source, say something like VCE SAT, you can just call it, and you can consider it like this. Similarly, for the diode, you can consider when the diode is conducting, there is a drop, you would say 0.7 volt, in power diodes it can be more than that, like these the anti-parallel diodes for IGBTs, it can be 1.5 to 3 volts and so on at higher current levels. So, you can represent this by some VD or actually VD in series with RD. So, for if you want it to be simple, it can simply be some voltage VD. So, these voltages will all be specified also in the data sheets. For example, in an IGBT data sheet, you will get this VCE, that is you will get it as a range. You would normally get the typical value under certain conditions, what would be the typical VCE would have been specified, and they would also specify what is called as the maximum VCE. So, you may get the same for the freewheeling diodes also, you may get the typical values and the maximum values. So, we can use these to come and to calculate these losses as we go further. Now, that is about the voltage drop. Now, we should know how much is the current going to flow through, etc. This is the voltage drop. So, what current is going to flow through that? It is the load current that is going to flow through the device. So, we need to understand what is the load current. Who determines the load current? It is the DC voltage and the modulating signals. So, I am considering sinusoidal modulating signals. There is some voltage VDC, I am considering some sinusoidal modulating signal. Incidentally, it is 0.8, like let us say 1 and minus 1 are the positive and negative peaks of the carrier, it is 0.8, the modulation index is 0.8, the sine peak is 0.8 times the carrier peak here, alright. So, this is sine triangle PWM, you have 3 sinusoidal signals for R, Y and B phases. Now, you have some load, this is being fed to a load. So, this represents the modulating signal actually represents the fundamental component of the voltage applied on the load, R phase of the load. So, let us say the load is an inductive kind of a load, RL load, it is a lagging power factor load. In this case, it is lagging by some 45 degrees, the load consumes certain amount of current, which is given by this thing. Of course, the load will have certain amount of ripple on top of this current waveform, and we are just ignoring this, and we have only the fundamental current is shown here. And you can see that the power factor angle is 45 degree, the load is lagging, the current is lagging the voltage by some 45 degrees now. So, if you look at who is conducting where, this is R phase, we are talking of R phase. So, R phase has got a top transistor, top device, bottom transistor, bottom device. Who conducts when depends on the direction of current. Now, for example, the current is negative here and the current becomes positive. Once again the current goes negative. This determines which transistor or which diode conduct, right. Let us just look at it now. So, this is what I have for you here. This is the same voltage source inverter. So, let us say the load current IR is flowing in this direction. The load current IR is flowing in this direction. So, how will it flow through? It will flow through this transistor, or it will flow through this diode. So, this top transistor, when your current is in this direction, this is only either the top transistor or the bottom diode will conduct. Sometimes the load current, let us call this as the positive direction of current. Sometimes the load current could be negative, that is it could be in the opposite direction. Let me just mark that in a different color. So, let us say this is the load current. So, who will conduct this load current? It is either the bottom transistor or the top diode. These are the ones that will conduct this load current. So, it is always one pair of one transistor and one diode. Which transistor and which diode, whether top transistor and bottom diode or bottom transistor and top diode, depends on the direction of current. That is what we are trying to make sure here now. So, this is what I mentioned here. So, this is what we have now. So, again whether this is the top transistor or bottom diode, that depends on what is the gating signal. If the modulating signal is greater than the carrier, then this is the top one. If the modulating signal is less than the carrier, the bottom one. That is what is illustrated here now. So, here you have the same R phase modulating signal and you have this R phase current shown here, and you are comparing it with a carrier. Of course, the carrier is shown to be of a much lower frequency. In practice, it could be much higher frequency than this. So, whenever the modulating signal is greater than the carrier, as we said in earlier lectures, this is going to be high, your PWM signal is going to be high. Therefore, you are going to have, it is the top one will conduct. Again here, when the modulating signal is less than the carrier, the top gating signal will be low and the bottom gating signal will be high. So, it is the bottom transistor or diode will conduct. Whether bottom transistor or diode conducts depends on the direction of current. So, from these two combinations you know who is going to conduct when. So, if the top transistor has been gated high and the current direction is this, then this conducts. For the same direction of current, if the top transistor is gated low and the bottom transistor is gated high, then this cannot conduct, this bottom diode conducts. So, same way if you look at the green direction of current, now if the top transistor is gated high and the bottom transistor is gated low, then this cannot conduct. So, the top diode will conduct. On the other hand, if the bottom transistor is gated low and the top transistor is gated high, then this current will flow through this diode. So, that is something first we need to know who conducts. So, only then we have to calculate, because we need to next calculate the transistor drop, the diode drop, and how much is that, and so on and so forth. So, let us look at it like this. Therefore, now if you go on, it depends on the sinusoidal modulating signals. This is Vm sin omega t, Vm sin omega t minus 120, Vm sin omega t minus 240. So, these are average voltages which we have seen before. This is the average pole voltage. R is the midpoint of the leg, O is the DC midpoint, VRO is what we call as pole voltage, VRO average is the average pole voltage. The pole voltage has been averaged over a carrier over a subcycle or a half carrier cycle, and what is that equal to? It is equal to MR by Vp times VDC by 2. If MR is equal to Vp, you can see it is VDC by 2. If MR is equal to minus Vp, you can see it is minus VDC by 2. So, this can go between plus VDC by 2 and minus VDC by 2. This is the average R phase pole voltage, this is the average Y phase pole voltage, this is the average B phase pole voltage. Now, the average line to line voltages are VRO average minus VY average. Similarly, VYB average, VBR average. So, then VRN average, if you consider balanced 3 phase loads, it is 1 by 3 times VRY average minus VBR average. And you would look at VRN average, what it would be? It would actually be this VRO average itself. This will be Vm sin omega t by Vp into VDC by 2. In case VRO average has some common mode, that common mode will not appear in VRN average as we see now. So, you have this kind of VRN voltage applied here. So, this voltage gets applied on the load and there is a certain amount of current that is flowing through the load. and that current, the power factor of that current also is important. The amplitude and the power factor of the current is important in determining your conduction as well as switching losses. Now, if you take an example which is more general, not just these 3 phase sinusoidal modulating signals, but there is also certain common mode component that is added, what is called as MCM. So, it is MR plus MCM, MY plus MCM, MB plus MCM, and this MR star, MY star and MB star are the actual modulating signals. You are comparing them with the carrier and you are producing the signals. So, what is your VRO average? It is not MR by VP, it is MR star by VP into VDC by 2. The same way this is MY star by VP into VDC by 2. So, as we have seen before, the advantage is that Vm can actually go higher, Vm can go up to 2 by root 3 times Vp. Normally Vm has to be restricted to Vp for sine triangle PWM. If you are adding common mode, an appropriate kind of common mode, then it is possible that Vm can be as high as 2 by root 3 times Vp, that is 1.15 times Vp. And even with a higher than that, like 1 to 1.15 times Vp, you can make sure that your MR star does not cross Vp. So, you would get something MR star, the peak value will not cross Vp. This increases the DC bus utilization as we have seen before, and your VRO average, VIO, RY and VRN expressions are given. Now, the difference you see is VRN average is Vm sin omega t by Vp into VDC by 2, which corresponds to this. The MCM is gone there. So, it is not exactly equal to VRO average. So, whatever is the common mode component or the triplet frequency components in VRO average, they have been knocked off, and that is what you get in the VRN average. So, many of these PWM things are like third harmonic injection, conventional space vector PWM, bus clamping PWM, all these are, there are different values of MCM are added in all these. So, this is just a quick recap of what has been done here. Now, we have to look at closely at the the loss. So, for that you need the duty ratios of the different phases, as we will see shortly. So, this is your R phase modulating signal, Y phase and B phase. I am once again considering 3 phase sinusoidal signals, then I am adding common mode there. So, what is my duty ratio of R phase? It is 0.5 plus MR star by 2 Vp. Let us say MR star is equal to Vp, then MR star by 2 Vp is 0.5, 0.5 plus 0.5 is 1. Let us say if MR star is 0, in that case dr is 0.5. Let us say MR star is minus Vp, in that case this is 0. So, for MR star going between minus Vp to plus Vp, dr goes between 0 and 1. So, this is level shifted here. The duty ratio of, what do you mean by duty ratio of R phase? We mean the fraction of the time for which the R phase top device is on to the total subcycle duration. So, if the top device is on, let us call it as T plus for a duration T plus, the bottom device is on for a duration T minus in one subcycle, then you can say this is T plus divided by Ts. So, this is for R phase. Similarly, in Y phase you will have the top device on for some duration and the bottom device will be on for the remaining duration. This is the duration for which the top device is on divided by the subcycle duration, and that has to be between 0 and 1. So, you can see that it is 0.5 plus My star by 2 Vp, and similarly the duty ratio here is 0.5 plus Mb star by 2 Vp. So, these are the modulating signals and duty ratios, and you need these duty ratios for calculating the conduction losses you are just going to see now. So, let us see what is that conduction loss. This comes because of this drop. If the transistor is conducting, if let us say a transistor in R phase leg is conducting, maybe the top, maybe the bottom. So, if it is conducting, it has a drop of VCE across that. Ideally this would be 0, but practical device has something. So, this VCE can actually vary with IR, but we are ignoring that here. We are saying that we are considering an IGBT where, we are ignoring that variation here, we are considering it to be constant. Ignoring what? Ignoring the variation in VCE with respect to IR. So, it is like saying that the on-state devices, during the on-state the device is modeled more by voltage source. So, this is like VC into IR is the instantaneous power dissipated in the transistor. Let us say a transistor is not conducting, rather a diode is conducting. So, the diode conducts what current? The same current IR, that is the R phase current, and what is the drop across the diode? Vd. So, it is Vd multiplied by IR is the drop across, is the power dissipated in the diode. Pd equals Vd/IR. Okay, right. Then what is your conduction loss averaged over a subcycle? These are instantaneously, it is different. So, this is VCIR, but the transistor is not going to conduct forever, not throughout the subcycle. How long does it conduct? It conducts only for the duty ratio. So, it is dr. So, dr multiplied by VCIR is the average power dissipated in the transistor on account of forward drop. Similarly, let us say the bottom diode is conducting for the remaining duration 1 minus dr times Ts. So, what is happening is, so how much is the average power dissipated in the diode? 1 minus dr times Vd into IR. This is the situation when the current is positive, when the top transistor is conducting and the bottom diode is conducting. On the other hand, when the current is negative, the bottom transistor and the top diode will conduct. So, you will have a difference in this duty ratio and 1 minus dr. So, you can actually write down the average loss over a subcycle, either for considering the positive or the negative. In most PWM cases, you do a symmetric operation. So, it is enough if you probably consider only one half, you do not have to consider both the half cycles of the current, you can just consider one half cycle of the current. And you can see that this loss is varying from one subcycle to another subcycle. Why? Even if we ignore this variation in VC may be 3 volts for some 50 amperes current, it may rise to 4 volts for some 100 ampere current. Let us ignore all that. Even if you have ignored all that VCE and you have ignored this variation in VD with current, you see that your duty ratio changes. If you have some duty ratio in this, like if your duty ratio is 0.6 in this subcycle, it is going to be something like 0.62 in the next subcycle and something like 0.635 or something in the subcycle after that and so on. So, this duty ratio changes from subcycle to subcycle and this current also changes from subcycle to subcycle. Strictly speaking, this current has both fundamental and the ripple component, but the ripple component can be neglected. We are talking of high switching frequency cases, it is not very significant. So, you can take this IR to be fundamental alone. So, this IR can be represented by some Im sin omega t minus phi as I had shown before. So, this is the variation. Now, if you call this as Im, the peak value is Im, this is Im sin omega t and minus some angle phi. So, this could be 45 degrees. So, you have IR varying and you also have the duty ratio varying with omega t. So, from subcycle to subcycle these terms vary and they vary like this over a half cycle, and the variation in one half cycle and the variation in the second half cycle are supposed to be identical, because that depends on if your PWM is done symmetrically. So, you should not have a problem. That is, let us say your duty ratio, maximum duty ratio is something like 0.8 and minimum duty ratio is 0.2. So, if the duty ratio in a given subcycle is D and or let us say some other number A, if A is the duty ratio in a given subcycle, after 180 degrees what would be the duty ratio? That should be 1 minus A. So, if you do that in a symmetric fashion, if the switching is done in a symmetric fashion, the losses are symmetric in the two half cycles, in the positive or negative half cycle. So, it is enough if you just consider, let us say one half cycle, say the positive half cycle here, and it is actually integrated over this. So, you take the average of this. So, this P conduction R what is given is the average conduction loss over a subcycle, and that is integrated over half a cycle or a full cycle to get your what is called as conduction loss. So, as I mentioned here, the variation of device drop may be ignored for simplicity. We can take the typical forward drop of the IGBT, and that would give a reasonable measure of what is conduction loss. But we want a safe measure, that is, when you are designing, you want to know the worst case loss, you want to be sure that the loss is not going to be more than so much. So, you could normally go by the maximum VCE. You can look at the maximum drop and by that you can calculate, that will give you what is called as a pessimistic figure, that is you will get a higher, your estimate could be on the higher side, but it is pessimistic. You can say that my conduction loss is not going to be worse than so much. So, you can use the typical value or you can use the maximum value to get actually a pessimistic estimate of doing this now, alright. So, you can also look at this VCE in terms of IR. If you say that you need a more precise calculation, what you can do is VCIR is available, that is available from the data sheet in some form or the other. So, this can be represented as a function of IR. So, which can be a curve fitting can be done, for example, if curve is available. So, then you can use that and you can still do the calculations and what could give you a more precise, but for simplicity I have ignored the variation. When you ignore the variation, what happens is VCE and VD come out of this, and then this is duty ratio. So, this duty ratio you can see that it is a function of your modulation index and omega t, and this current is a function of its peak amplitude, some what we can call as capital Im, and again fundamental angle and power factor angle. So, these are the two things that you have here. So, you integrating, you take the average, you are going to get the whole thing as a function of modulation index, the peak value of current and the power factor angle of current. So, with this simplifying assumption, when you take VC and VD to be constant, it is possible for you to evaluate the conduction loss in one leg pertaining to any PWM method, and you can get an expression for that. The expression will be in terms of the modulation index, will be in terms of the peak current, load current, and in terms of the power factor angle. So, it is possible to get this down here now. How does one PWM to another PWM vary this? That is obvious from here. So, you may have an inverter which may be operating with PWM method 1. The DC voltage is fixed, the modulation voltage is same, and the AC voltage is same, and the AC side current, power factor are all same. But what is different? The PWM method is different. Because the PWM methods are different, the line harmonic currents are going to be different. Let us ignore the harmonic current, that is not significantly affecting the conduction loss. But what changes significantly is the duty ratio variation changes. Sometimes this duty ratio may be a sinusoid above 0.5, which may be a sinusoid plus 0.5 in sine triangle PWM. In case of other PWM methods, it will be 0.5 plus sinusoid plus some triplen frequency component added to that. So, this dr changes from PWM method to PWM method as a function of omega t, and like what I had said before, here it is 0.5 MR star by 2 Vp, and this MR star is different from PWM method to PWM method. So, since that MR star varies from PWM method to PWM method, your dr varies from PWM method to PWM method, and therefore, the conduction loss will vary. But how much will it vary? It is always the transistor or the diode is conducting. So, the variation is not much, it is only to the extent of the forward drop between the two. For example, if let us say the transistor has a forward drop of 3 volts and the diode also has a forward drop of 3 volts, it does not matter at all, not very significantly. So, still the conduction loss would vary over some band, but the switching loss will vary much more significantly with PWM methods, as we will see in the next lecture, or we will get a feel for it even by the end of today's lecture. Alright. So, now you go for PWM method by PWM method. I said that this procedure is common for anything now. So, it is not just sine triangle PWM. What I have done is, on this modulating signal, I have added common mode for all the 3 phase modulating signals. So, your R phase signal looks like this. So, the common mode signal is a third harmonic signal. So, that is why I call this as third harmonic injection PWM. We have seen this before. Now, what should I do? The duty ratio I must calculate based on that. What happens in the duty ratio? It is the same nature of curve. Here 0 becomes 0.5, that is essentially the difference, and this is 0, 0.5 and 1. You just change the scale and draw, and now this MR star will give you the duty ratio. So, you can calculate the duty ratio. Once you calculate the duty ratio, it is possible for you to calculate the conduction losses. Once again, as I said before, you can calculate the conduction loss as a function of modulation index and your current amplitude and power factor angle. So, this is conventional space vector PWM. Here in third harmonic injection, you are with sine triangle PWM and all that, the 0 vector time is there, you apply both the 0 states, and it may not be for equal duration. In conventional space vector PWM, you are adding this kind of a common mode. It is not a sinusoid, it is not a third frequency sinusoid, but it is what looks like a triangular carrier, but it is not triangle, it is actually half of this sinusoid. This is half of this sinusoid, and this is half of this sinusoid, this is half of this sinusoid, and what goes here is half of this sinusoid. So, you take the middle value of the 3 sinusoids and take 50% of that and add that as common mode, and that gives you conventional space vector PWM, as we have seen before. The resultant modulating signal is like here, and your Vm can go up to 1.15 times Vp, as we have already discussed. So, how does the duty ratio vary? The duty ratio variation is given by this modulating signal. So, with this duty ratio variation, it is possible for you to calculate your conduction loss. Now, let us move on. This is generically for the third harmonic injection PWM. So, as I mentioned, it can be anything, MCM, and third harmonic is some k times Vm sin 3 omega t, where k is a fraction, like k can be 0.5% or 10% or 15% or 20% or 25% or some small number like that. So, what you can do is with third harmonic injection, what we have seen before is the peak value of the modulating signal is lower than that of the sine. Therefore, Vm can be greater than Vp without pulse dropping. Higher AC voltage can be produced than what you can produce with sine triangle PWM, and this is what we mean by DC bus utilization. So, k equals 1 by 6. If you take this k to be 1 by 6, that is the amplitude of the third harmonic is 1/6 that of the fundamental, you get the highest possible AC voltage, which is 15% higher, greater than sine triangle, and k equals 1 by 4 yields the lowest harmonic distortion. So, this is the 1 by 6 which has been illustrated here. Actually, it is about 2 by root 3 is your sine peak, is 2 by root 3 times V peak, and with the common mode added, you can see that your modified common mode MR star just touches 1, it does not go beyond 1. So, you are within linear modulation and you are able to produce this PWM, it is the highest DC bus utilization. With third harmonic injection, your common mode or the total harmonic distortion is minimum, waveform quality is best when you add k equals 1 by 4. That is, the third harmonic amplitude is 1/4 of the fundamental, which is kind of illustrated here now. So, for these methods, all these methods, you can go by calculating the duty ratio from these modulating signals and you can calculate your conduction loss. So, this is we have seen continuous modulating signals. Similarly, you can have discontinuous modulating signals. There could be discontinuous functions of time, and which we call them as continuous and discontinuous PWM schemes. What are examples for continuous PWM? Sine triangle, third harmonic injection, conventional space vector PWM, these are all examples of continuous PWM. What are examples for discontinuous PWM? The different kinds of bus clamping PWM methods, which we will anyway quickly again look at now. So, now in bus clamping, what happens? Every phase is clamped to one of the DC buses over certain intervals in a line cycle, and that is typically the phase is clamped to the positive DC bus for 60 degrees and to the negative DC bus in another 60 degrees. So, the modulating signal is a discontinuous function of time. Then you have several such modulating signals are possible. This is what we have seen before, and now we are going to relook at one and see what is the problem with the so called 120 degree clamp PWM. What is being done? There is a 3 phase modulating signal. Now, you are adding a common mode, and the common mode added is like this. So, the common mode is always positive. So, what happens? This goes and hits the limit at +1 during this interval for 120 degrees continuously, and the modified modulating signal comes like this. So, what is the effect? You can see that the duty ratio is 1 here, but the duty ratio never goes to 0. So, here the top device is continuously on, whichever one might be conducting. Let us say the top transistor, let us say if the current is unipolar, the current direction is such that it is the top transistor should conduct. What happens? The conduction loss in the top transistor is going to be very high, and the conduction loss in the bottom transistor is not going to be that high, because the first half and the second half of the modulating signals are not really symmetric. The loss in some subcycle here and the loss in some subcycle here are not going to be equal, and the loss in the top device and bottom device are going to be unequal, and that is a problem with this 120 degree clamp PWM. This is the other 120 degree clamp PWM. Here what has happened is you have added this kind of common mode component, which is always negative. So, here the bottom devices tend to conduct for longer than the top devices. So, you can see that the bottom duty ratio is always 1. So, you may have more conduction loss in the bottom device than the top device. So, it is unequal. So, when you are adding this common mode, we have to make sure that the top and the bottom devices are balanced and the losses in all the 3 are balanced. So, if you want to make sure that top and bottom are balanced, what we have is this is the positive clamping common mode signal, and this is the negative possible common mode signal. You can either follow this or follow that. If you follow only one, you lead to one 120 degree clamp, and you lead to this also leads to another 120 degree clamp, both are bad. You need to follow this for 60 degree, follow this for another 60 degree, follow this for 60, another 60, this is for 60, other 60. So, that is what you need to do to get a balanced loading of all of the devices. Now, which 60? That is the question. It can be 0 to 60 here and 60 to 120 here, 120 to 180 here and 180 to 240 here. That is one possibility. That gives you one PWM method. Or it can be, let us say, 20 degree to 80 degree here and 80 to 140 here, 140 to 200 here. That gives you another PWM method. So, it all depends on which 60 you choose and which 60 you choose here now. So, one simple example. So, those are many variations. What we try to do is the common mode signal should have a periodicity of 120 degrees. it must contain only triplet frequency components. So, it will follow the positive common mode for 60 degree and the negative common mode for 60 degree, and it will also have a 0 average value. So, if you, this is what we would do to come up with most of the popular bus clamping PWM methods. This is one popular bus clamping PWM method which is called 60 degree clamp. So, this is the sinusoidal modulating signal for R phase, and the common mode added is like this, and therefore, the resultant R phase modulating signal is like this, and you can see that the R phase is clamped here for 60 degrees. So, it is the top is continuously on, nothing else. So, here the bottom is continuously on, here again it is clamped. So, you see that it is symmetric. Whatever is done at theta, if your duty ratio is D, the duty ratio is 1 minus D here, and whatever happens to the top device, the same thing happens to the bottom device 180 degrees later. The conduction is all, I mean the losses are uniform in all the devices, alright. So, this is one example of 60 degree clamp. How do you actually evaluate the conduction loss? The same procedure. Now, the duty ratio is given by, if you have this modulating signal, and that gives you the duty ratio. The duty ratio is 1 here, the duty ratio is 0 here, and this is 0.5. So, if you use these duty ratios and substitute in that expression, it is possible for you to calculate your conduction loss. Again, this is again 60 degree clamp, which is illustrated for 1 is equal to 1.1547, that is 1 m is equal to 2 by root 3, that is the modulating signal has a peak value 2 by root 3 times the peak of the carrier. So, in this case, the modified modulating signal just goes and touches 1 and stays at 1 and comes down. If you go little above this, it will go into what is called as over modulation. So, this is the highest possible thing, and again how will you do it? With the duty ratio only. The procedure is same. Now, the duty ratio variation is as shown by this now, right. So, this is continual clamp PWM, that is 60 degree clamp was a particular case of this. This is a little more generalized. So, what we have now clamped is, we have now clamped between 60 to 120, but earlier we had clamped, now we are clamping between 30 to 90, and again here we are clamping it between this 210 to 270. So, this is again here there is a different modulating signal, this gives you the duty ratio, you can go by this duty ratio to calculate your DR. This is another clamping. So, everywhere once you know the modulating signal, you can find out the duty ratio, how the duty ratio varies as a function of omega t, and you can do these calculations. So, all various examples. So, for all the various bus clamping PWM methods, you can just do this exercise. So, this is a split clamp PWM. What happens is that it is not clamped continuously for 60 degree, it is clamped for some 30 degree here and 30 degree here, and so we call it 30 degree clamp PWM here. So, here again if you want to calculate the conduction loss, you can see that the duty ratios go by this now. Okay. So, everywhere you can see that the same way, this is another split clamp where it is not, conduction is not 30 and 30, but this is something and this is something, they add to 60 degrees. So, for example, this could be 20, this could be 40, I mean I see that it is 50, this is 10, this is 50. So, again this is 10, this is 50. This is, the waveform looks asymmetric, that is actually quarter wave asymmetric, it is not half wave asymmetry. So, whatever is you have the waveform value at theta, at 180 plus theta it will be the negative of that. So, whatever happens to the positive device here, the same thing will happen to the negative device later. So, it is all symmetric, it looks lacks quarter wave symmetry, but as I mentioned before, it is not bad at all. In fact, such a split clamp PWM gives you a better harmonic distortion than this nice looking 60 degree clamp PWM. Alright. Now, we are anyway talking of conduction loss. So, for anything if you have the modulating signal, you know this, you have the duty ratio as a function of angle, and you can calculate the conduction loss per leg, that is the bottom line. Now, if you want to do the same thing using space vector based PWM. So, of course, for continuous and discontinuous PWM methods, you can construct the method as an equivalent modulating signal, and you can do that, that is always fine. But let us anyway look at it from this point of view also. You have a revolving reference vector, you are sampling it in once in every subcycle time, and then you are going to apply this vector for t1 seconds and this for t2 seconds and the null vector for tz seconds to realize this vector in an average sense, we know this. So, this is how you do your volt second balance. So, Vref is applied, Vref over Ts is what you need. So, you apply V1 for T1 seconds, V2 for T2 seconds and Vz for Tz seconds, such that T1 plus T2 plus Tz is Ts. So, you have maintained your volt second balance. How much is your T1? Calculated. How much is your T2? How much is your Tz? These are given here. So, you are going to do this. This is space vector based PWM. So, if you look at Vref, for example, you look at space vector based PWM, what happens is the inverter states are applied like this 0, 1, 2, 7 and the R phase switch is like this. Once again, to calculate the conduction loss per leg, what we needed there was the duty ratio. You can actually express the duty ratio here, duty ratio of R phase, that is the time for which the R phase is on, divided by the total subcycle duration. So, what is that? It is on during this 0.5 Tz plus T2 plus T1 divided by Ts, that is the duty ratio of R phase. What is the duty ratio of Y phase? It is 0.5 Tz plus T2 divided by Ts. What is the duty ratio of B phase? It is simply 0.5 Tz by Ts, and this T1, T2, Tz all can be calculated using a Vref and alpha. So, in case you want to do it like this, you can also express your duty ratios like this. So, you can, if you can come up with your 3 phase duty ratios over a sector, it is same as arriving at the duty ratio of every phase over an entire cycle, because the sequences are going to be used symmetrically in the 6 sectors. So, if you want to look at it from the space vector point of view, then this is how the duty ratios can be evaluated. Again, if you are looking at the switching sequences from the space vector point of view like this is bus clamping sequence 0, 1, 2, 2 and 0. You are using only the 0 state 0. What is the R phase duty ratio? The R phase duty ratio is T1 plus T2 by Ts. What is the Y phase duty ratio? Simply T2 by Ts. What is the B phase duty ratio? 0. B phase, it is minus VDC by 2, it does not switch at all. The top device is never on. So, it is 0. Similarly, if you look at the sequence 1 to 7 or 7 to 1, the top R phase is always on, the R phase top device is always on. So, that duty ratio is 1 and dy is given by this duration T2 plus T7 by Ts and dB is given by T7 by Ts. So, if you are conventional or any bus clamping methods, you can also look at them like this and evaluate your duty ratios and you can go by doing it, alright. Now, if it is advanced bus clamping PWM, once again you need the duty ratios. So, how do you get your duty ratio? If you look at your duty ratio of R phase, it is 0.5 T1 plus T2 plus 0.5 T1, which is nothing but T1 plus T2 divided by Ts. What is your Y phase duty ratio? The Y phase is switching twice, but still what is its duty ratio? It is on, the top is on for T2 seconds out of the Ts. So, it is T2 by Ts. What is the duty ratio of B? It is dB is equal to 0. So, if it is 0, 1 to 1 or 1 to 1 0, these are the 3 phase duty ratios and these are same as what you get for 0, 1, 2. These are actually same as what you get for 0, 1, 2. The same way you have the other advanced bus clamping sequences 1, 0, 1, 2, that is this 0.5 T1 can be shifted ahead here. So, you can have 1, 0, 1, 2 or 2, 1, 0, 1, this can go there. So, for those sequences also you will find the duty ratio is same. So, though a particular phase switches twice, it is the duty ratio, this duty ratio for 0, 1 to 1 or 1, 0, 1, 2 is same as the duty ratio for 0, 1, 2. Similarly, if you look at the sequence 7 to 1, 2, so here R does not switch at all, duty ratio is 1. What is the Y phase duty ratio? It is T7, which is basically Tz plus 0.5 T2 plus another 0.5 T2 divided by Ts. So, it is T7 plus T2 by Ts. What is duty ratio of B phase? It is T7 divided by Ts. So, here again this duty ratio is actually same as your duty ratio of 7 to 1, 1 to 7. The same thing can be said about 2, 7 to 1 also. So, even if you have these kind of switching sequences, you look at the space vector base. So, for advanced bus clamping PWM, what you can do? You can actually calculate your switching sequences based on this. I mean you can calculate your duty ratios of the different phases based on this, and you can use these duty ratios in your whole expression. If you evaluate this dr dy dB over the entire sector 1, it is equivalent to having evaluated dr over the entire line cycle because of symmetries, right. So, you can evaluate this and you can use that in your conduction loss expressions, and it is possible for you to evaluate conduction loss for advanced bus clamping PWM also. Thus, we have now looked at how exactly the conduction loss can be evaluated for sine triangle PWM and third harmonic injection, space vector PWM, etc., for bus clamping PWM or discontinuous PWM, and we have also seen how you can possibly do it for the advanced bus clamping PWM. So, as I mentioned, it is not very, it varies, the conduction loss varies with the PWM method, because the duty ratio varies with PWM method. If you go back to that expression, you can see that the duty ratio varies, but that variation is not very high, but the switching loss you can see that it is much more significant, because this duty ratio varies, but the switching loss is much more. Let us quickly see how. In all these, this is some continuous modulation. What happens? there is always a phase switches once. So, sometimes the phase may be carrying a high current, let us say the power factor is near unity. So, the modulation, the fundamental voltage is high, the duty ratio is high, and the phase current is also high, the phase is going to switch now. Here the phase current is going to be low, but still the phase is switching once. Here again the phase current will be high, though in a different direction, the phase continues to switch. So, phase switches everywhere, whereas if you go to some bus clamping PWM method, let us say here the phase does not switch here. So, during this time the switching energy lost in that phase is 0. Similarly, during this interval the switching energy lost is 0. If it so happens that the current is also having a peak here, then you are never switching the phase when the current is high, and therefore, you will save a significant amount of switching energy loss, particularly when your power factor, load power factor is high. So, that is really the essence now. So, that depends on what kind of modulation signal you use, and it depends on your load power factor. And so, this is best for unity power factor load. You will be able to avoid switching the phase when it is carrying the highest amount of current. Again, here also it is when it is carrying highest amount of current. So, this method for example will be very good if your load is at a leading power factor. If your load peak current occurs exactly here, it is actually very good, but if the load is lagging power factor, it may not be good. On the other hand, this is good for load with lagging power factor from the switching loss point of view. What I am trying to say is the conduction loss is influenced by PWM methods, but not so much. Switching loss is influenced even more by PWM methods. So, you have these many things, and we will discuss all this in the next class in considerable detail. And when you look at here also, for example, here what happens is you have some switching energy loss, here you have some energy loss in both these devices. If you look at the conventional sequence, you have all the 3 devices undergoing switching once, and there is some energy lost here, whereas if you look at here, one does not undergo, this undergoes some switching energy loss, this undergoes 2 losses, one on and one off. So, if it so happens that this phase is switching lower amount of current, then and this phase is switching a higher amount of current, then you gain by switching this phase twice and clamping this phase. So, these are some methods we use to so we can employ the sequences depending upon which phase is carrying higher current or lower current or whatever, and it is possible to design some PWM methods using these sequences to reduce your switching loss. These are certain things which we will see in the rest of this module. So, these are certain references which are there for your quick this thing. So, this is a PhD thesis and this is another paper, and this is yet another reference. So, this would help you some things on the losses, particularly these two ones, loss and the junction temperature estimation, and I would discuss this more, give you more references in the next lecture. And thank you for your interest, and I hope you will continue to follow these lectures. Thank you very much.